I saw in the program 20, that's one. But I guess that's with questions.
That is with the questions and change. Yeah.
All right. Hi everyone. I'm Efstatios Gavves. I'm from the University of Amsterdam. First of all, I would like to thank you for the invitation. And today I would like to present about the machine learning of time in videos. So first I would like to start with the problem. What's the problem? From my point of view, of course. So to me it's quite unclear what's the role of time in spatiotemporal sequences. And I take a step back. I'm not calling them videos. I call them spatiotemporal sequences. So what's the difference? In my opinion, image models work well for two reasons. First of all, they rely on convolutions. So before convolutions, neural networks are just classifiers. Convolutions are spatially stationary signals, and images are spatially stationary signals. Convolutions work only with stationarity, so that bodes well. And second of all, backprop. Well, it works well if you've got full supervision and millions of labels. For images, that's quite easy, or quite easy by now. In videos, things are quite different. So temporal stationarity is hard to guarantee for long and complex videos. So when you've got like small temporal changes, temporal stationarity can be guaranteed, basically because we can have millions of videos again. But when you're increasing time, then this breaks. This means that short convolutions are not enough. Instead, in my opinion, modeling temporal transitions is the way to go, so directly, which is in fact quite hard for several technical and conceptual reasons. So I'll present some works of mine very briefly. I've got 15 minutes only then. So first of all, I'd like to discuss a video graph, which is ongoing work with my student, Nuruddin Hussein, and Arnold Smoller. Well, he's not my student, he's my boss. So first of all, complex actions. What's complex actions? Preparing breakfast takes several like seconds or minutes. In Epic Kitchen, you've got like long videos, very nice videos. These are longer complex actions. Stirring food is a one action or unit action or what have you, because basically you can, you only need 2 frames. What are characteristics of complex actions? They're long range, which means they can span like several seconds or minutes. They've got temporal extent, so the unit actions that they're composed of might vary in duration, and they've got temporal dependencies, so you've got to learn basically how things are connected. Now a year ago we had timeception. It was presented in CVPR this year, and basically timeception proposed an efficient modular layer. Modular means that you can stack, and stacking means that you have large temporal receptive field, effective temporal receptive field. This allowed to have temporal on-convolutions. So basically we threw away everything spatial. Temporal on-convolution means that your convolution is even shared across channels or across semantic channels. So it's basically you're learning on and off what changes and multiple scales. Now timeception charades had very nice results. We could process 1,000 frames per video now from a single model without averaging, of course. Previous models can do the same, but with averaging. So that's the result, which led to better accuracies. So yeah, by increasing the time steps by tenfold, we could get significant improvements. So the insight was that longer range temporal relations are important. Now the question is, how can we go even longer? Stretching time. The idea, a great idea, we think, is to have time as a graph. So what does this mean? The nodes are sort of key one actions or temporal concepts, if you like, whereas edges represent temporal affinity between those actions. Now, why is that a good idea? Because then you can have sublinear temporal representations, as nodes are temporal concept clusters. You don't have to put all the frames in your representation. Similar or irrelevant frames are discarded and scales up to hours-long videos, hopefully. It also increases interpretability because the graphs are discrete and it's quite straightforward to reason. How video graph works, you've got to have the frames with the 3D CNNs. Then you've got a node detention layer and some concepts that you're learning on the fly. Then the transitions become some like concept vocabulary, which are then clustered together into graphs, graph embeddings. and then classified. So how does the graph embedding works? We're learning a set of latent concept representations from randomly initialized points. Dot product is used for similarity, so this is basically attention, that's node attention. And we're reweighing all learned concepts by the activations. So in experiments that works quite nicely, so we get a bit better numbers and we're working to improve them. We're beating our previous work, timeception, by a bit. What's very nice in my opinion is that we've got interpretability. So basically, so all these clusters, they have a semantic meaning. Of course, we attach the meaning afterwards, after we inspect the videos or the concepts that we've learned. So making serials means has something to do with cereals and with, well, food box and with eggs. That makes sense. Now, that was the first work. So how to stretch time. A second very important question, my favorite in a way, is how we can actually represent time in neural networks, in models. So one idea is time-aligned nets, or how you can use neural network layers as time steps. And it was presented last year in BMVC, together with Amir Gothrati and Kay Snook. Oh. Okay. So some properties, basically we start with some properties of time. You know, what makes time so unique or like so distinct in videos. So we don't claim that this is a complete set, by no means, but some of them is temporal symmetry. So forward or reverse arrow. As you correctly said, that's not always the case. Actually, in many cases in UCF, it's really hard to, even for a human, to basically tell the difference. But you can definitely say that there is a temporal symmetry in that a video is by definition going forward. There is temporal causality, so things cause each other in a video. There is temporal continuity. So here we stop a video and then you see that it's already weird. So temporal continuity means that the frames have to be resembling. And there is temporal redundancy, which is together with continuity. Now, some dominant approaches are what? LSTMs and 3D convolutions. LSTM learn these transitions that I mentioned at the beginning, whereas 3D convolutions are learning spatiotemporal correlations. That's what they literally do. They're not even causal. So what happens when we're running LSTMs and C3Ds on an arrow of time task? Well, this is what happens. We took the TSNE embeddings and we visualized them, natural versus reverse. And as you can see, basically they completely overlap each other. So this means that these two models do not really learn time-sensitive representations. Now, of course, it's a question whether we need time-sensitive representations. That's another question. But assuming that we want to have a temporal learning, ideally we would like to have them separated. Now, why is that the case? Why is this happening for LSTMs? Like, they work so great for language. Well, recurrent networks are highly sensitive dynamical systems, as Pascal and Benji showed in 2013. And they're very sensitive even with highly discriminative symbolic data language tokens, like one-hot vectors. Now, this means that the gradients are very sensitive to initialization, and you got poor learning and no generalization. Basically, when you change a bit here, the initialization, then your embedding at t time step can go completely different. Now, why is that the problem for visual features? Because they're much noisier than symbolic data. They are much less discriminative, and they're much more redundant. So learning LSTMs on videos is orders of magnitude harder because you're having chaotic regime, no useful gradients, and then the learning doesn't really happen. And then what we observed in practice in this work was that forward and backward LSTM, or even shuffling frames, well, basically it gave the same accuracy. Now, as a proposal, we proposed time-aligned neural networks. So the basic idea was, if components are so much better in vanishing and exploding gradients, which is one of the problems, why is that the case? Well, convents can handle vanishing and exploding gradients because basically they do not share parameters over abstractions. So you've got no parameter sharing, no iterated maps. So the iterated maps in the recurrent networks create the chaos and therefore the problems. So the premise also the premise of LSTM parameter sharing is infinite Markov chains. In practice, we chop that, right? Like we're going to take t steps back. so why not do it with a convnet instead? So as an idea, why not flip the convnet from that, like that, and then each layer becomes a time step. And this is what we did. So basically this looks like an unfolded recurrent neural network with unshared parameters. And the good thing now is that we have no vanishing or exploding gradients and no problems with noisy and redundant input, because convnets are, as Jan said very nicely, they've got this very nice inductive priors that make things work even in these cases. Now when we recheck the arrow of time, we get nicer results with the time-aligned dense nets. So basically, this is LSTM, things overlapping, C3D also overlapping. Where with time-aligned dense net, you actually get the nicer separation, not perfect, but nicer, between forward and reverse. This shows that basically you've learned something about time now. Again, this doesn't mean that you're going to get higher UCF scores or kinetic scores or whatever, but it shows that you've learned something about time. A conclusion is that poor temporal modeling is likely due to hard and thus unsuccessful optimization. Because at the end of the day, this is not super different from a recurrent network other than having non-shared parameters. Last, I'm in time almost. I would like to present one more work with one slide only for a specific reason. Well, it's spike neural nets. It's actually many works. It's a very nice and exciting field, so I'm just putting it for your awareness in case you're interested to find more about them, and they're very much related to the keynote presentation. So these works are with my student Peter O'Connor and Max Vellen, and they were published in iClear. Now, what are spiking nets? Well, the motivation is basically that most sensory data is temporally redundant. And for today's model, temporal redundancy is a bug. So we actually sample frames far away. For spiking models, temporal redundancy is a feature. That's how they live. And they've got great promise of human brain-like efficiency. So basically, if that's your temporal signal, ideally you would like to have a spike only when things change. Now, unfortunately, following the programming analogy, unfortunately, spiking networks are still in the pre-alpha release stage, so they don't really work. And there are some big problems that cause this. One is how to backprop through spikes. That's not easy, because the spikes are by definition discrete. And backprop needs by definition differential functions. Also, in theory, if you want to be super technical about it, you have to backpropagate to infinity for spiking neural networks, which is clearly creating a lot of problems. And if you don't believe what I'm saying, that's our experiments to publish a paper, MNIST. So the problem is so hard that even with an MNIST experiment, you can publish. It also means that it's super hard, right? Myself, I'm saying that these are not super convincing results, but maybe that's not the point. So, in my last 1.5 minutes, I also add the what is missing slide and challenges. So basically, we are here, in my opinion, we've got too much image, or otherwise called space-only focused models. So if that's our image problem space coordinate system, our images are here, and our videos are here. And then, as we know, the further we go from the center, the curse of dimensionality or of problem dimensionality increases. Now, I believe that we should have a spatiotemporal problem coordinate system. We should transition to models focused on the spatiotemporal problems. This requires a deeper understanding of the role of time in spatiotemporal sequences. The role of time means longer sequences. If you've got short sequences, you can run your convolutions. You've got temporal stationarity. That's, I wouldn't say necessarily solved, but we know the recipe there. Long sequences, however, means temporal non-stationarity. So this has to be solved. And also it means that you cannot have labels. You cannot have labels for a million frames for a million videos. An idea and my intuition is that maybe what we're doing wrong is that instead of currently we're putting neural network, the time in neural networks as input or as output. We append an extra time channel, or we predict time and whatnot. maybe what we need to do instead is to put time in the neural network structure. Now that's hard, that's different, that's hard. Just having an extra, okay, sorry, it's done. Just having an extra dimension, that's easy. But redefining the structure of neural networks, it's actually uncharted territory. Now there is, for instance, the geometry in deep learning. It doesn't deliver great results, but it's, it's a direction. Second of all, I believe that there is a great need for a tighter community and better communication channels, because conferences are growing so large that it's hard to even spot relevant papers. And this initiative, is a great step forward. And also, I think we need more balanced data sets. So everybody believes in data sets. That's not in doubt. But first of all, video is not only action. And I don't think to get better video understanding, we need better action understanding. We also have to take care that we have a trade-off. I mean, we have a trade-off between larger data sets bringing better performance, but also larger data sets making it harder to train and compare equally. So maybe having a temporal property, spatial temporal decathlon, where we actually compare well thought of properties makes sense. Thank you.